Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of car reviews from Edmunds.com, and we're going to try to predict the rating of a given review based on the actual review text along with a few other features about the review. So let's get started. Hop into the notebook here. We're going to use a Keras neural network today to make our predictions. Down here I'm importing NumPy and Pandas just NumPy and Pandas just for working with the data. And then these are our pre-processing libraries and functions. We're going to use regular expressions, the stop words from the natural language toolkit, the Tokenizer from keras.preprocessing.text, the pad sequences function from keras.preprocessing.sequence, the train test split function from sklearn.model_selection, and the standard scaler from sklearn.preprocessing. And then we're going to use TensorFlow to actually build the model, and we'll use the sklearn metric r² score to evaluate the performance afterwards. So I'm going to go ahead and import those, and we can load in the data using pandas.readcsv, and we can get the CSV file path up here, review.csv. So I'll paste that in, and we can load it in. Alright, so let's take a look at the data. It's a fairly simple data set. We have a good number of training examples, and as much as I would love to use all the data here, it was training quite slowly. Just the whole pre-processing as well was quite slow, so I'm just going to limit the number of rows we're using today to, I'll use 20,000 at first, and then maybe at the end we can scale it back up. So I'm just going to use 20,000 of the rows. So here, and I realize we're probably missing out on some of the different companies and models. So actually, maybe we can do something a little different. Instead of specifying the number of rows here, we take the data and we'll sample it. Data is good. We're going to rewrite data to be data.sample fraction. How about we take? We'll take a third of the data or so. We'll take 30% of the data. And that's going to be without replacement, so that we won't get duplicate examples. So we run that and take another look. We should only have about 89,000, which is a much more reasonable number. And we also have a mixed amount of different models and companies. All right, so why don't we reset this index here? Reset index, drop equals true. Drop equals true just prevents the old indices from becoming a new column. So I'll reload this data, then we'll sample again, this time resetting the index, and we can take a look. Alright, so here's the data set we're going to use with 89,000 examples. And I want to get some more information on the data set, so I'm typing data.info. And we can see we have some sort of missing values here. We have 89,714 total entries, and there are a few columns here that have not that many non-nulls. So that means there are some missing values. Alright, so let's start pre-processing. So we're going to use a bunch of different helper functions today, but I'm going to start with a pre-process inputs function that's going to take in the data frame. It's going to make a copy of the data frame, and for now all it's going to do is return the data frame. Now we can get the process data down here. So we're going to process data, and we'll store the processed version in X. And so X is currently just a copy of our data, but as we pre-process it, now we can see the result down here. So the first thing I'd like to do is actually drop the reviewer column. And the reason for this is there's a really high number of unique values in here. We can actually double check that if we just check x.unique, and we take the length to count the number of unique values. Oh, sorry, this should be x subreviewer dot unique. So we have 70,000 unique reviewers out of 89,000 examples, and we're just not going to get much information from that. We also want to sort of build a model that doesn't rely on knowing who reviewed it to make a prediction. So I'm going to drop this column by just saying, okay, drop reviewer column, and then df equals df.drop reviewer from axis 1, which is the column axis. Now reviewer is gone, and I believe we're going to use all the rest of the data. So rating is what we're trying to predict, and I would like to use the actual text information in the review, because I doubt that we're going to get, maybe if we just use the title would be okay, but certainly from these features we're not going to really get a good sense of the rating of the review. We definitely want to include the actual text. So to encode text is a little different from usually how we encode a column. We can't just one-hot encode this review because each one of these is unique, so there'd be no information gleaned that way. However, we can encode each word separately and try to train a model to make predictions based on what kind of words are in the review. For that, we're going to use a few different methods. But the first thing I'd like to do is actually remove any any rows with no review. So let's just check this. I'm going to call data.isNA to see the missing values. We can sum over the rows to get the total number of missing values in each column. You can see we have 32 missing values for reviewer, but we actually dropped that. We actually have no missing reviews. I believe if we use the full dataset, there are some missing reviews. So yeah, I'm just going to include it anyway, so that if we wanted to do the whole dataset, we can. So I'm going to remove rows without reviews. So we can get the missing reviews, or the rows with missing reviews, by taking df sub review, then getting its isNA matrix. Well, it would be a vector in this case. For example, let's do it for, yeah, I guess we'll just do it for review. We do data sub review, and then .isNA. This will be true and false, where a true means there's a missing value there. We can actually use that true-false series as an indexer for data, like that. And you can see we actually don't have any. Let me use the log function. I'm going to use that as the row indexer, and I want all columns. You can see there aren't any examples, but if we went ahead and used the full dataset, there would be. So I'm just going to proceed as if we're using the full dataset. So let's do that down here. I'm going to take that isNA, and I'm going to use it as an indexer for df, as the row indexer. And then I'm going to take the index of that data frame to get only the row indices that we want to drop. And then we call df.drop on missing reviews axis 0, because it's the row axis. And anytime we drop rows, we would like to reset the index. Again, I'm going to specify drop equals true. Alright, so that was a bit unnecessary for our purposes, but if you want to use the whole dataset, I want to leave this in so that we can. Alright, and then I'd like to fill missing titles. So you see we have 6 missing title values with an empty string. And the reason we do this is because when we want to encode the title as a sequence later, we actually can't have a missing value in there. It has to be a string. So all I'm going to do is take the title column, call fill NA on it, which will fill any missing values with whatever value we give it, and I'm giving it an empty string, and that'll do it for all missing values, just be encoded as empty string. Alright, and now I'd like to process, so do some preliminary processing for the title and review columns. So I'm going to create another function up here called process texts. It's going to take in a series of texts, so it's going to be panda series. We'll either pass in the title column or the review column into here. And when you're using, we're going to use an embedding layer, word embeddings, which is sort of using deep learning to learn representations for the words. And when you're using that, you don't have to do really too much like manual processing of the text, because the model can learn the relationships between the words on its own. However, we're going to do some basic processing, nothing fancy. I'd like to remove stop words from the text, which are just the most common words in a given language. And I'd like to remove digits. I'd like to not confuse the model with numbers. I just want to remove any digits as well. So why don't we do this? I imported stop words at the top from Natural Language Toolkit. And stopwords has a words function. We pass in a language, and it will give us back all the stopwords in that language. And so in our function, I'm just going to use this right here, and I'll call it stopwords. So stopwords is a list of stopwords for the English language. And the reason we want to remove them is because they often don't contribute much to the meaning of the sentence. They're present in almost every sentence, and they don't flavor the review in any meaningful way. And having more words can slow down your model as well. I'd like to actually create a copy of texts before we proceed. Alright, so the first thing I'd like to do, I noticed that these reviews were not new line. I mean, they have new line encodes, new line characters, or escape characters here, \n. I'd like to just replace that with a space, because there's really no reason to have that there. So let's do that first. So I'm going to apply a lambda function to our texts, which again could be either the title column or the review column. And x here is going to represent a given title or a given review. And what we can do is use regular expressions to process out various aspects of the review. So let's use this as an example. I'm going to head over to regex101.com, which is a fantastic way to test out regular expressions on a string. And I want to remove a \n column. Now, for regular expressions, we actually, if you're trying to remove a given sequence, like an actual set of characters that is always present in the same way, we don't really even need to use regular expressions for this. I'm going to anyway. We just literally type in the thing we'd like, and this isn't working because we have to escape the new line. We have to escape the backslash with another backslash. And then you'll see it is targeting any \n's. So I want to use this regular expression to substitute \n's with a space. So we're going to transform x, which is going to be a given one of these, into regular expressions.substitute. The expression we're using is that double \n, and we're going to replace it with a space, and we're going to apply this to every x in texts. So this will essentially replace any new line characters with a space. Alright, we'd like to do a similar thing now, except a different expression and a different replacement. We'd like to remove digits, so any digits like this. How about we use this one? Just bring this in here. So I want to target all digits in the expression, and the way to do this is with \d. \d will target digit characters, and we can add a plus to mean any number of times in a row. So now you can see both have been targeted. So we're going to use that up here, and then we're going to replace it with nothing. We just want to delete it out of the string. So that will remove digits, and then last thing I want to do is do the stopwords thing. So this one's a bit more involved. I'd like to, okay, here's what I'll do. I'll apply a lambda function as well. For every x, I'd like to, well, x, remember, is a review, so it's a string of words. I'd like to split it on whitespace, then check each of these words that we split, check if they're stop words, remove the ones that are stop words, and then join them back together. So I'm going to first create the list that I want to split. First I'll do x.split. And I want to go through x.split now. I want to iterate through x.split. So we'll use a list comprehension here and iterate through for every word in x.split. for every word in x.split, I'd like to throw the word into this list. However, I only want to throw the word into this list if a certain condition is met, if the lowercase version of the word is not in stop words. So if the word is not a stop word, we'll throw it into the list for every word in x.split. And then once we have this list of all the words that aren't stop words, I'd like to join it back together on whitespace. So this will remove stop words. And that's all I'm going to do. We'll return text after that. We can practice this now on X. So let's take the review column and try to process it. Process texts. And it might just take a moment while it goes through each one. It shouldn't take too long though. Alright, it finished. And you can see we no longer have those numbers anymore. The digits are gone. The stop words are gone, so the sentences don't make as much sense anymore. And as well as additionally, the new line characters are gone too. There was one right here, and you can see, well, we can't actually see it, but those have been removed. So, yeah, that's pretty good. I'd like to note that when we tokenize this sequence of words now, we're going to use the Keras Tokenizer for that. All the punctuation will be removed. Everything will be set to lowercase, and it will be split on whitespace. So essentially, the rest of the pre-processing will be taken care of by the tokenizer. All right, so let's do that then. Let's create a function now called getSequences. And getSequences is also going to take texts. This time it's going to assume the texts have been processed already. And we're going to create a tokenizer. And this is going to be the tokenizer from Keras.preprocessing. And we'll specify a number of words to use. Now we can put this number up, maybe 20,000, 30,000. Basically, it's the number of unique words to allow into our sequences. For our purposes, I'm going to keep it rather small, just so we don't slow down the model too much. For the sake of time, I'm keeping only 5,000 words. So we're going to use the top 5,000 most frequent words in the reviews and the titles to create our sequences. And then once we've specified that tokenizer object, we'll call tokenizer.fitOnText. Here we pass in texts, and then we'll generate our sequences. So the sequences can be generated from tokenizer.texts to sequences. And this just takes in texts as well. And now if I return this, return the sequences so we can see what it looks like. Let's say I want to get the sequences for the titles. So that's X subtitle. Oh yeah, okay, there's actually missing values there. And I didn't fill them here. Wait, didn't I fill the review? Oh, let me do this. Let me run it again. Shouldn't. Okay. Alright, so here are the sequences. So essentially what it did is it took each word and checked it in a word index. And the word index is generated from the tokenizer.fitOnText. So this function essentially goes through the text, finds each unique word, and checks the frequency of each word. And then it assigns each word to a number, to an integer, based on frequency. So a 1 represents the most frequent word, 2 represents the second most frequent word, 3 represents the third most frequent word, and so on, up until num words, so 5,000 words. And then it actually this text to sequences function converts each word into an integer that represents it. So we can actually check here. I want to see what this number 1 is. So that's the 1, 2, 3, 4, 5th example, and that corresponds to car. So it makes sense that car is the most frequent word. and you can see that that is present in the third example as well. I mean the fourth example. So there enough, you can see car is there. Alright, so this is good. This is a nice way to encode our sequences of words. However, the only issue here is that they're all of varying length, and TensorFlow is not going to like that if we try to pass it in like that. So the last thing we'd like to do here is pad the sequences with zeros to ensure they're all the same length. So for that, we can use the pad sequences function, again from Keras.preprocessing, which I imported at the top. So we can say sequences equals pad sequences of sequences. Now we have to specify a maximum length to pad. And to get the maximum length, I'd actually like to find what is the longest sequence in this whole list. And so to do that, if we want to get the maximum sequence length, we can start by taking sequences and map a function to it. So we'll use a map here. Map just maps a function to a list, and the function we want to map is a lambda function that's going to map x to length of x. So for each sequence, we're just going to change the sequence into the length of that sequence. And then once that's all done, we can take the max with numpy.max. Now I would like to note we have to convert the map into a list before we do that, so that's all we have to do. And this will return the maximum sequence length of our sequences. Once that's done, we can print out the maximum length just so we can see max sequence length. And that will be max sequence length. I guess I'll also include just a new line so we can see them on separate lines. Maybe not. Okay, that's fine. Alright, now we can include the maximum length as max sequence length. And now we can pad the sequences with zeros accordingly. Now I just like to include padding equals post so that the zeros go on the end of the sequence instead of at the beginning. Alright, and we run this, and let's try getting the sequences now. Alright, and you can see the maximum sequence length is 29. So these are actually, this is an array of the number of examples by 29. So there's 29 values across each row, and each one of these represents a different title. And we could do this for review as well. I'm expecting a longer maximum sequence length for the review since we have whole sentences here instead of just a short title. Alright, and finished with a maximum sequence length of 2055. So each one of these is of length 2055 now. And we know for each of these there's 5,000 unique different words. That was what we specified. Alright, so these are actually ready to go into our model. They're ready to be fed in as inputs. So let's put this on hold. What we'll do down here is we'll process the title and review columns using our process text function. So df subtitle equals process texts of df subtitle. And similarly for the review, it's the same thing, just using using review instead of title. Alright, once that's done, we can get the sequences. I'll say get title and review sequences and drop original columns. So I'll store the title sequences in titles, and that will be get sequences for df subtitle. And then I'll store the review sequences in reviews, and that will be get sequences for df sub review. And then I'll drop both of those columns because we don't need the original columns anymore. So we're going to drop title and review from axis 1. Okay, we're getting there now. Actually want to comment this out just because every time we run this, it's going to take a long time to get the sequences. So I'm just going to, we'll uncomment it later. Now I want to work on the rest of the data. So if we look at this now, X should just be like all of the data. Yeah, let me comment out the process text as well. That's taking some time. What is taking time now? I did run this, right? There's no reason this should be taking so long. Just dropping some. Am I calling any functions here? No, okay, that's it. Alright, so here's our X. This is the rest of the data. Now, for company and model, these are nominal features. So they're categorical features that do not take any, the values within them do not take any sort of ordering. So the proper encoding scheme for such features, assuming their cardinality is not too high, if the number of unique values is not too high, then the proper way to encode them is with pandas.getDummies or some other way to get dummy columns. So let's look at company. We'll get the dummy columns for X sub company. Now it's going to send each company to its own column, and we will get a one-hot vector that represents the original value of an example. So you can see here we have a 1 for Volkswagen, and that corresponds to the value of the original example. So if we look over here, you can see that's what we're seeing here. That corresponds to this 1. All the rest are zeros, and this will add 46 columns to our dataset, but we will effectively encode the column. Now model, I think, has a few more columns, 858 unique values, so each one gets its own column. And you know, it's not really a big deal. This is still a reasonable number of columns to add to our data. If it were in the 10,000s, I probably would just drop it for our purposes. But since this is only 800, I'm going to keep it on. So we'll create a function up here, one hot encode function, that will take in a data frame and a column. It will create a copy of the data frame. Then it will create the dummies with pandas.getDummies for df sub column. And I'd like to point out that on our dummies, if we wanted to specify a prefix, that will just add a little model. It will say model at the beginning of each of these column names, and that allows us to know like where these columns are originally coming from. Because if we just had a column called 200, we wouldn't really know what that meant. But if we see it says model 200, then we know, oh, that's from the model column. So I'm going to include the prefix on is the same as the column name in our function. So prefix equals column. Alright, and then we'll actually concatenate the dummy columns to the original data frame. So df equals pandas.concat df dummies, and we're concatenating along axis 1, so side by side. Then we can drop the original column from which we created the dummies, since we no longer need it, and we'll return df. So we're ready to encode these guys. The last thing here I need to worry about is the date column. So for date, if you look up here, we have 2 missing values in here, so we'll have to figure this out. Basically, you can use pandas.toDateTime to take in the date column, and well, let me try it on a single date. If we just pass in a date as a string, it'll return it as a datetime object. And what's nice about a datetime object is then you can type .year to get the year, .month to get the month, .day to get the day, and so on. And so we can actually use that to extract out each bit of information from the original date column and put it in its own column, which will then be a numeric feature. Now the problem is when I pass in x sub date here, we get an error because there's some string in here that is not properly encoded. Someone maybe entered in a bad date, or it's just not in a format that toDateTime can pick up on. So when this happens, there's a few ways you can do this. You can specify the errors parameter, argument, which basically says what to do when we handle an error. Now, by default, it's on raise, which will, again, raise this error. There are other methods. One is ignore, in which case it will do the encoding, but then those bad strings will still be in there, and I don't really want that. So the last one is coerce, and this will turn the bad strings into NAT objects, or not a time objects. And the nice thing about that is then we can go ahead and fill those missing values accordingly. Alright, so this is the coerce version, and I'd like to use this in a new function called Encode Dates. And Encode Dates will again take in a data frame and a column we'd like to encode. It'll make a copy of the data frame. Then it will take the column and you call pandas.toDateTime on the column. And we want to include errors equals coerce. Then once we've turned it into a datetime column, I'd like to extract out the year, month, and day features. So we'll create a new column for each. The first column will be review year, and review year will be composed of the original column with a lambda function applied that goes through each x in the column and returns x.year. And then we can do the same thing for month and day. So this will be review month, and this will be review day, and over here this will just be x.month and x.day. And once we're done, we can drop the original date column from which we created these new 3 columns, since we no longer need it. And that will encode our dates. So let's do this. Let's say extract date features, and df equals encode dates. We pass in the data frame, and the column we'd like to encode is date. Now we'll take a look. It could just take a moment, since you saw that using errors equals coerce actually takes a bit of time. But it should be done in just a moment. Here we go. You can see year has its own column, month has its own column, and review the day has its own column. The original date column is gone, and we know now there's some missing values in these 3 columns. So now it's easy to go in and fill those in with the means of the columns. So let's do that. Let's say fill missing date values with column means. So we're going to impute the values using the means of each column. So for each column in review year, review month, and review day, we're going to take the column and call fill NA on it, passing in here df subcolumn dot mean. And then we're going to store that in the original column. So now we're going to fill in each of these with the proper, with the means of each one. Alright. So now let's one-hot encode. Let's do the one-hot encoding for company and for model. So one-hot encode company and model columns. So we're going to use our one-hot encode function that we created. That takes in a data frame and a column. We're going to encode company, and then we'll do it again for model. Alright, now let's take a look at this. Alright, so here it is. You can see we have the original data here. And then at the end we have all the one-hot columns. So we have a total of 909 columns now. And if we look at how many missing values we have, with isNA.sum, so we're summing both over the rows and the columns to get the total number of missing values, we have no more missing values in the dataset. So here is a nice clean dataset that we can feed into our model. The last thing I'd like to do is actually scale the data so that each column takes on a similar range of values. And we'll be using a standard scaler, which will give each column a mean of 0 and a variance of 1. And so over here, first, I'd like to split df into x and y, since I don't want to scale the rating column. This is what we're trying to predict, so I don't want to mess with those values. And we can call y df sub rating, and x is going to be the rest of the data that isn't the rating column. So we're dropping it from axis 1 and storing that in x. Alright, and then we'll do our train test split. So the train test split will give 70% of the data to the train set and 30% to the test set, and we'll use the test set to evaluate the model. Now, so I'm going to not just split x and y, I'm also going to split the titles and reviews. So this is the part where I'm going to uncomment these. And I'm going to split our titles and reviews into train and test sets along with the x and y, because we want to feed these in as inputs along with our x. So what I'll do is I'll create titles train and titles test. I'll extend the logical line here with a backslash, and then reviews train, reviews test, again extending the logical line, then x train and x test, and finally y train and y test. And all these are going to be split using the train test split function from sklearn. Here we just pass in each one we're splitting, so the titles, reviews, x and y, and x and y. And then we'll specify a train size, so I'm going to use 70%. We'll include shuffle equals true. This is on by default, but I'm just going to keep it there so you can see. It's going to shuffle the data and then do the split. And because there's some randomness involved there, I'd like to include a random state to ensure the shuffle, and therefore the split is always done in the same way. Alright, so now we'll scale the data. We're only scaling x. I don't want to scale the titles, reviews, or y. Just worrying about x here. And scaling the data can really improve the performance of some models, especially neural networks. They really benefit from the data being scaled. So let's create our scaler. This will be a standard scaler that again is going to give a mean of 0 and a variance of 1 to each column. And we'll call scaler.fit on just the train set. So I'm only fitting it to the train set because, we're only fitting the model to the train set, and you sort of want to pretend you don't have access to the test set at the time of pre-processing, because in practice you wouldn't have the test set available. So we're only fitting to the train set, and then I'm going to transform both the train and test sets using the fit we have to the train set. So I'm calling scaler.transform. Here we're passing in x train, and here we're passing in x test. And this function actually does return a NumPy array, so I'd like to turn them back into data frames after to give it that, so we can visualize it more nicely. And then I'm going to include the index. I want to keep the indexes the same. This should be x test. So because when we recreate the data frame, the indices get reset. So including this will keep the indices the same. And the column names as well I'd like to specify. That can just be the same as x.columns. Alright, and so this is it. That's all our pre-processing. We're now going to return all these values here. So alright, so we're returning all these values, and we'll get those values down here. So you can see we have 6 sets of the data. 2 of them are the titles, 2 of them are the reviews, 2 of them are the x's, and 2 of them are the y's. And those are all coming from this single function that could just take a moment to load in. But we'll take a look at some of that data. I want to look at titles train. I want to look at reviews train. Maybe the shapes of them will be more informative. And I'll look at xtrain.shape, and finally ytrain.shape. Alright. Alright, it finished, so let's take a look. Alright, so for each of these we have 62,799 examples. That just corresponds to the 70% of the original data that we got from the train to split. Then we have 18 sequences of length 18 for our titles, sequences of length 1099 for our reviews, an input vector of length 908 for our x, and then our labels is just a single value, so there's a single one-dimensional vector corresponding to the ratings for each one. Now I'm going to treat this like a regression task where we're going to try to predict the rating on a continuous range. So we're going to start our modeling now. And so we have 3 different sets of data we'd like to input to our model. And like I said, we're going to use word embeddings to embed these sequences. So again, look, the sequences look like this. They're sequences of data. We're going to use something called a word embedding to send each of these words to its own spot in a vector space. And we'll do that using the tf.keras.layers.embedding layer. So the embedding layer is really cool. It takes in an input dimension, which is essentially how many unique words do we originally have. The reason it takes that as an input dimension is because you can think of, let's look at the I guess titles train. You could think of each of these words as imagine one hot encoding, one of these. If we want to one hot encode this, I think we could actually do it if we turn this into a data frame. If we turn this into a data frame and then get the dummies for it, pandas.getDummies, we'd have to get it for each. Alright, let's just do it for the 0 column. You can see each value goes to its own thing. This isn't going nowhere. Basically what I'm trying to say is if we're looking at titles train, we know there's 5,000 different values in here. And so if we wanted to encode a single one of these as a one-hot vector, we would need a vector of length 5,000 to describe that, where each location in the vector represents a different word, and we'd have a 1 in the location of the given word, and zeros in all the other places. So the sparse encoding, that's the one-hot encoding, would be of length 5,000. And so the input dimension is basically the length of the sparse encoding. So we include 5,000 here. And this 5,000 is really only because we specified 5,000 here in the number of words to use. So the input dimension is the length of the sparse encoding. And then the output dimension is the dimension of our dense encoding. And this is what we get to choose. We're going to send each of these words to its own location in a high-dimensional vector space. So how high a dimension is up to you. I'm going to use 64, but this is a hyperparameter that you can tune to try to optimize the model. The higher it goes, the longer the model will take to train. I'm going to use 64 for now. But basically what that means is we're going to take each of these and send it to its own place in 64-dimensional space. And that's nice for many reasons. One, because we don't actually have to know where to send it. The model has weights that will actually determine where it goes. So it's actually learned. The representations are learned instead of having to manually encode them. In addition, it's nice because we only have to encode each word as a vector of length 64. Whereas if we used a sparse encoding, we would need a vector of length 5,000, which would significantly reduce the power of the model, or rather the speed, the performance. I don't know if the performance would be inhibited. It might be, because it might overfit more easily because we have so many features. But mainly the time it takes to train would go down a lot, would go up a lot. All right, and then the last thing we should put here is the input length, which is just going to be the length of a given sequence. And so this is determined by which, if we're doing titles or if we're doing reviews. So I'll save this for a moment. and I'd like to focus on the inputs to our model. So we're going to have three different inputs. One for the titles, one for the reviews, and one for the X's. So I'm going to send them each, I'm going to have their own sections for each. We'll have the X inputs, the title inputs, and the review inputs. And each one of these is going to be given by tf.keras.input, and we specify the shape here. The shape is always going to be a vector. In the case of a one-dimensional input, you consider the input for a given training example. And so it's always going to be the second dimension of our shape. So here it's xtrain, here it's titles train, and here it's reviews train. Dot shape sub 1. So the reason here is you see, if we look at the shape of this, the length of a given sequence is 18. So if we do sub 1, we just get 18. That's what I'm putting in here. For xtrain, that's 908, and for reviews train, that's 1099. So that's the length of our input for each of these inputs. And then for the X's, what I'm going to do is just do a simple two hidden layer neural network. So we'll have our first dense layer, call it dense 1, be tf.keras.layers.dense. Number of neurons here, I'll just keep it at 64, but because I don't want to go too hard into optimizing this model. It's quite a complex model. And then we're going to pass in X inputs here. So it's going in, being fed into the dense layer. Then we'll create a second dense layer. I'll call this dense 2. And this takes input from dense 1. I should give these all names, actually, so that we can visualize it nicely later. I'll call this X inputs. I'll just call them the names of the name equals dense 1. And here, name equals dense 2. Alright, over here, our name is title inputs. And lastly, over here, our name is review inputs. Alright, so we basically have finished for the X's. We're just doing a simple thing for this. Now for these ones, we want to use the embedding layers. So we'll have title embedding and review embedding. And each one of these is going to be a embedding layer. So like that. The input dimensions are the same for both of them because I left that the same. They both have 5,000 unique words in them. Output dimensions can be the same, but if you wanted, you can change these to different values. The input length here is going to be the length of an input, so I'm just putting that there. And here the input length is the length of an input, so I'm putting that there. Alright, now the embeddings are going to output the same sequences, but where each word has been encoded as a 64-dimensional vector. So you have a matrix of length, sequence length by 64. It takes in a single vector of length, sequence length, and returns a matrix of sequence length by 64. So because we have a two-dimensional output from our embedding layer, we're going to want to flatten the output to store it back into a one-dimensional form. So stack all the rows of the matrix into a single vector. And I would like to first include that we have to take input from title inputs. In the bottom we do review inputs. And then we'll have our flatten layers. So the top will be title flatten, the bottom will be review flatten. This is review. And then each of these is going to be tf.keras.layers.flatten. I should give these names as well. The name will be, on the top it will be title flatten, bottom will be review flatten. Alright, and then I'll give these names as well. Embedding, this one is title, this one's review. Alright, and then last thing to do is take the outputs from each of these sections So let me just separate them. And then we're going to take the output from the x's, the output from the titles, and the output from the reviews, and concatenate them all together in a single concatenation layer. That's tf.keras.layers.concatenate. And then we take in the output from x, which is dense2, the output from title, which is title flatten, and the output from reviews, which is review flatten. And we'll give that a name as well. Call it concatenate. And then we'll have our outputs. So the outputs is going to be a single dense layer with a single value output, which is going to be the predicted rating. And because this is on a continuous range, we just have a linear activation, which is another way of saying no activation. Alright, and now we can visualize this model. So I'll create the model with tf.keras.model. We specify the inputs here with 3 different inputs. That's going to be these ones: x input, title inputs, review inputs. X inputs, title inputs, review inputs. And then our outputs is just going to be the single outputs layer that we have done here. I also noticed I forgot to include the input here, which will be concat. Alright, and then we'll print out a summary of the model and plot it with tf.keras.utils.plotModel. You can see, oh, we have a problem. None type is not subscriptable for concatenate. What does this mean? Oh, I see what the problem is. I forgot to input into my flatten layers. So the title flatten layer is taking input from title embedding, and the review flatten layer is taking input from review embedding. Okay. Alright, here we go. So this is what our model looks like. We have 3 different inputs. They all go through their own version of encoding or being, different methods of calculation, and then they all the results get concatenated together, and then that is sent to a final dense layer with a single output, which is the predicted rating. You can see in here, this is the embedding, which takes in, for example, in the title embedding, it takes in an input of length 18, returns a matrix of 18 by 64, where each one of these 18 is represented by a vector of 64 dimension. Okay, so let us now start training. You can see why I went through the trouble of making all the names so that we can see them here on the diagram. Alright, so training. So first let's compile the model. I'll use an atom optimizer. And for loss, we'll just use mean squared error since it's a regression task. Then I'll store the fit history in history and call model.fit. For the inputs, we need to pass in 3 different values. We're going to pass the x train, the titles train, and reviews train. That's our input. Our output is just y train. And then we'll give it a validation split of 20%. We'll specify a batch size of maybe 32. We'll train for a bunch of epochs, but I will include a callback function that will stop it early. tf.keras.callbacks.early stopping. That will monitor our validation loss. And after a certain number of epochs, if the validation loss does not improve, we can specify how many epochs here. Let's say 5. So if the validation loss does not improve after 5 epochs, we will stop the training and restore the weights from the best epoch. So restore best weights equals true. And run that. And while that's training, we can create results here. So I'd like to get the loss and the r-squared score. So for a regression task, r-squared score is a good way of understanding how it's doing. It basically measures how dispersed the data is around your fit. So our loss will be taken from model.evaluate, and we're going to evaluate it on the test set. So our input here is x test, titles test, and reviews test, and our output that we're comparing it to is y test. And I'm going to include verbose equals 0 so that we don't see the loading bar. And then R2, our R squared score, is going to come from the sklearn function R squared score. And that takes in a set of true predictions, the true labels. So that's our y test, meaning like the correct answers to the prediction task. And then it's going to take in a set of predictions, which we can get from model.predict. And if we just want to predict on the test set, we pass in x test, titles test, and reviews test. And I'll also include verbose equals 0 here, so we don't see the loading bar. Alright, I'll wait for this to finish, and then I will press enter. Actually, I do want to print out the results like this. Test loss, display it to 5 decimal places, and format with loss. And then we will do the same thing but for the R squared score. And I'll format that to 5 decimal places and format with R2. And I'll just indent this nicely. Alright. Alright, it finished. Note that the best epoch was actually epoch 1. So it started overfitting extremely quickly. You can see the training loss is always going down, but the validation loss started going up immediately. So this might be solved, maybe, I'm not sure for sure, but by some sort of regularization. So maybe we could try some batch normalization or dropout layers in our model. I'm not going to go into full optimization though. And I guess we can get a sense of how this is going down here. So we can get the loss and the R squared score for our test set. Yeah, it just calculating. Alright, we got a test loss of 0.5, which is more on par with our validation loss on the best epoch. And then we have our R squared score of 0.486. So this is not such a bad R squared score. It's definitely not perfect. The best R squared score you can get is 1.0, but it can get a lot worse. It can actually go deep into the negative numbers. So an R squared score of 0.48 is not terrible. And I guess that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.